In this video, we're going to take a look at duration. There's a previous video that I did that talked about how to calculate duration and introduce the idea of what duration was. In this one, we're going to start looking at how we can use duration to predict bond price changes. We're going to introduce the concept of convexity and how that introduces a little bit of error in our prediction of bond price changes. And we'll also introduce the idea of an immunization strategy. Now, there are a couple of handouts in this video that I'm going to go through that are probably going to be pretty hard to read on just the video. So I'd encourage you to go through and download the template from Google Docs. It's just at tinyurl.com, Brocker duration 2, and that way you can have that to follow along. Might be helpful to work through some of the examples, and also, like I say, some of the charts and tables that I'm going to introduce in here are a little bit small, might not get captured quite as well in the video. It would be handy to have it with you that you can look at a little bit closer. First thing we're going to look at is how to use duration to predict changes in bond prices. And so we've got this nice little formula here that says the change in bond price is equal to negative duration divided by 1 plus K times the change in K, where K is the market rate of interest. Now, a couple of quick things on here. First of all, this change in bond price is a percentage change, not a dollar value. Second thing is that notice we take duration divided by 1 plus the market rate of interest. This is sometimes referred to as modified duration. In the previous video that I went through calculating duration, we had a couple of formulas to calculate duration, and those calculated what is referred to as Macaulay duration. In order to convert it to the bond price change, you get a little more accuracy if you use modified duration, where you take duration divided by 1 plus the market rate of interest. Now, in that previous video, there was another formula called effective duration that we used. That's already sort of a modified duration, so you don't need to make this conversion if you're using the effective duration calculation. And then we multiply by the change in the market rate of interest. Now, note this negative sign up here. That's to capture the inverse relationship between market rates of interest and bond prices. If interest rates go up, bond prices should come down. So this negative is going to flip around the interest rate change to get us back to the bond price change. So let's go through an example. You have a 10-year 8% coupon bond. Current market rate of interest is 7.25%. Now, in this video, to save a little bit of time, it's already a rather long video, I don't want to calculate duration, so I already did that and just provided the value. So duration is given as 7.32 years. If interest rates fall by 80 basis points, what will happen to the bond price? So let's go ahead and walk through that. Go ahead and rewrite the formula up here. The change in the bond price is equal to negative duration divided by 1 plus the market rate of interest times the change in the market rate of interest. Now we just want to plug in our values. In our example, our duration is 7.32 years. Our market rate of interest is 7.25%. And here you want to make sure you plug that in as a decimal. So it's not 1 plus 7.25. We don't want to divide by 8.25. We want to divide by 1.025. And then by the change in the interest rate. And here we say interest rates are going to fall by 80 basis points. That's 0.8%. It's a fall in interest rates, so our interest rate change is negative. Interest rates are declining. Now we just grab our calculator, go through the calculations. You should end up with a change in the bond price of 5.46%. Now, one thing to keep in mind is that's the change in the bond price in percentage terms, if we want to figure out what the bond is going to be worth, we have to first of all know what the starting value is so we can multiply by 1 plus the change in the bond price. So real quick, if you want to do that, assume annual interest payments. We had 10 years to maturity. We said the market rate of interest was 7.25% as our starting point. Remember, we're solving for the original bond price, so we're solving for the present value. Was an 8% coupon bond, so that means $80 a year in coupon payment. And lastly, we have the par value returned to us at maturity, so that's going to be our future value, $1,000. Let me quick go through that calculation. That gave us a starting price of $1,052.07. So we said, given this change in interest rates, the bond price should increase by 5.46%. So that's just our starting point. Allow it to increase by 5.46%. And we're going to predict the new bond price to be $1,109.51. So that just goes through our prediction using duration to predict the change in the bond price. Note that duration says the bond price will rise by 5.46%. That's just what we did. Assuming the original assuming annual coupon payments, that bond was originally valued at $1,052.07. We showed how that calculation was done. So duration predicted that the new bond price, when interest rates drop by 80 basis points, would be $1,109.51. However, if we actually calculate the new bond price, all we have to do is say, well, if interest rates change overnight, there are still 10 years remaining until maturity. Now, the market rate of interest dropped by 80 basis points. So instead of 7.25%, it's now going to be 6.45%. We're solving for the present value. Bond price still has an $80 coupon payment and a $1,000 future value. So we grab our financial calculator, plug these values in, solve for the present value, and what we're going to come up with is $1,111.69. Notice that's not what we predicted from duration. Duration said it should be $1,109.51, and in reality was a couple bucks higher. Now that's not a big error, but it still is a little bit of an error. So what went wrong? Is our duration messed up? Did we screw up a calculation somewhere? The answer is no. Instead, this is what we're talking about when we're talking about convexity. Duration is not a 100% accurate predictor of bond prices. It's an approximation. That approximation is better for small interest rate changes. Here you can see this is one of those reasons why I said you might want to print this out. Some of the text in here is kind of small to read, but here we're looking at a 30-year 14% coupon bond. This is just an example to show you convexity. So we're looking at a longer term high coupon bond here. And what we see with the convexity is this is the actual bond price. This reddish pinkish line here is what's actually happening. When interest rates go down, the bond price goes up. When interest rates go up, the bond price goes down. This bluish line here is the duration prediction. Duration says as interest rates go down, the bond price will go up. Interest rates go up, the bond price will go down. But note, duration predicts a linear relationship. This is a straight line here. This is a curved line. The actual bond price is convex. Duration predicts linear. Actual bond price is convex. What that means is we're going to get some errors. Note this is our starting point here, 0%. If we have a 1% change, not a very big change in the bond price, you can see the duration prediction is real close to the actual bond price. For small changes in interest rate, duration is a very good approximation. However, what happens when we get to big swings, when interest rates rise by 4% or interest rates fall by 4%? We start to see that the duration misses by a lot more. So one of the issues with convexity is that duration works better as a predictor of bond price changes for small interest rate changes than it does for large interest rate changes. Now, another thing to note when we look at duration and the concept of convexity is that not all bonds have the same degree of convexity. For example, this graph here that I'm looking at is a 30-year bond. Notice quite a bit of convexity out in the extremes. Here's another graph with a 5-year bond. Now notice when we look at this one, remember this is just a 5-year bond, still same 14% coupon rate. But notice the convexity here, the errors are much small, even out on the big swings in prices. So one of the things we note is that all else equal, shorter term bonds are less convex. Duration will be a better predictor for short term bonds, and longer term bonds are more convex. Duration will be a less accurate predictor for long term bonds. Another factor that plays a part is the coupon rate. Now, both of these bonds, I used a high coupon rate, but convexity also differs based on the coupon rate. All else equal, the lower the coupon rate, the more convexity the bond price will be. So duration is a less accurate predictor for a 0 coupon bond than it would be for my 14% coupon bonds that I'm looking at here. So a quick summary of convexity. Remember, actual bond prices are convex, they're not linear. So that's going to introduce error from our duration prediction. How much error depends on the bond. All else equal, the higher the duration of the bond, and remember, long time to maturity means high duration, low coupon means high duration, so a longer time to maturity and or a lower coupon payment is going to mean there's going to be more error. The bond is more convex, and so duration will be less accurate. Duration works best for short-term high coupon payment bonds. It works worse for long-term low coupon payment bonds. Another issue that we talked about, the bigger the change in interest rates, the more error there will be. Duration is a great tool for estimating small changes in interest rates and seeing what impact they're going to have on bond prices. It's not as good of a tool for looking at big percentage changes. If you want to see what happens if market rates of interest change by 50 basis points or 100 basis points, duration is going to give you a pretty good approximation. If you want to see what happens when interest rates change by 400 basis points, duration is not going to be near as accurate. Now, one other issue with convexity that I want to talk about a little bit is what happens when there's a call provision. So let me go ahead and just draw a quick graph here. Pretend those are straight lines. I have a little bit of artistic challenges. And a normal convex bond looks something like that. You can see that it's not a linear relationship. As interest rates decline, bond prices go up more rapidly. As interest rates go up, bond prices fall at a slightly lower rate. However, let's think about what happens when there's a call provision. In a call provision, typically the issuer is going to choose to call the bond if interest rates fall. Just like refinancing a mortgage, nobody wants to go out and refinance when interest rates go up. They want to refinance when interest rates come down. And the call provision gives the bond issuer a way to do that. They can buy back their bond for a fixed price and then reissue bonds at lower interest rates. However, remember, a call provision means the issuer gets to buy it back at a fixed price. So the bond price isn't going to keep going up, up, and up. when interest rates decline, because investors are going to start to figure out, hey, this bond isn't going to mature. Instead, it's going to get called. So what we're going to see is a relationship that looks more like this. Because the call price is going to cap off the value of the bond as interest rates fall, we won't see that full convex relationship. Instead, we'll see a kinked curve where it's concave at low interest rates. Call provision is going to prevent it from keeping to go up, and then convex at higher interest rates. So convexity just works a little bit differently with callable bonds, something to be aware of. Now we're going to switch gears. Instead of talking about convexity, we're going to talk about immunization. One of the things duration can be used for is to talk about how bond prices change when interest rates change. How sensitive is the bond price to interest rate changes? Another thing that it can do, though, is help us balance off price risk and reinvestment rate risk. Remember, the reinvestment risk means if I have a 10-year bond and interest rates go up, maybe my bond price is going to drop a little bit, but I can reinvest those coupon payments at a higher interest rate. So from a reinvestment rate perspective, increases in the interest rate are beneficial to me. Decreases in the interest rate mean I can't reinvest those coupons at as high of a rate of return. Price risk is the normal bond price interest rate relationship that we talk about. When interest rates go up, bond prices come down. When interest rates go down, bond prices go up. So if I look at, for example, a 10-year bond, if I only hold that bond for, let's say, 1 year, then price risk is going to be more important, because I'm not going to have much time to reinvest my coupons. By the time I get my coupon payments, I'm selling off the bond. But when I sell that bond, it still has 9 years remaining till maturity, so it's going to be very sensitive to interest rate changes. Instead, if I hold that bond for, let's say, 9 years, now the reinvestment rate risk is going to be more important. And the reason for that is when I sell that bond, there's only 1 year left to maturity. It's a short-term bond. And we know short-term bonds aren't very sensitive to interest rate changes, so it's not going to be affected. The price will not be affected much by what has happened to interest rates. On the other hand, I've now had several years to reinvest my coupon payments. So if I've got a 9-year holding period, then the reinvestment rate risk is going to be more important to me. If I've got a 1-year holding period, the price risk is going to be more important. And you can see somewhere in between there, they're going to balance each other out because they counteract each other. Increases in interest rates are good for one and negative for the other. Duration helps us find that holding period. The duration tells us the holding period where price risk and reinvestment rate risk offset each other. So here I did an example, and again, this is going to be too small to really look at closely in this video, but I'll just walk through it a little bit. Hopefully you'll look at it in a little more depth. But what I did was I started with a bond, and I forgot to write down the time to maturity on this bond, but I'm trying to remember, I think it was like a 30-year bond, and it had a duration of 12 years. So if we have a bond with a duration of 12 years, what happens then as interest rates go up, we're starting out with an 8.5% return. As interest rates go up, I can reinvest these coupon payments. So what I'm doing is it's a 7% coupon bond, and that coupon payment that I receive in year one, I get to reinvest now for 11 years. Because remember, I'm going to hold it for 12 years, I sell it off, so I reinvest that for 11 years and it's worth $189. Next year I get another coupon payment, reinvest that for 10 more years at 9.5%, it's worth $173. When I sell the bond, I can sell it for $782 because interest rates went up, the bond price went down, it's not as valuable to me. But when I add up all the cash flows, the reinvested coupons and the price that I can sell it at, after 12 years, I'll have total cash flows of $2,240.87. What about if interest rates dropped? If interest rates drop, Notice I don't get as much for reinvesting my coupons. Now I'm only getting 155 for reinvesting that coupon 11 years compared to the 189 I got before. I only get 144 for reinvesting this second coupon for 10 years, and so on. But when it comes time to sell the bond price, now I can sell it for more. So sum these all up. And notice very close answers, regardless of whether interest rates went up to 9.5% or down to 7.5%. The total future value is the same. So that's what we mean by immunization. If I hold that bond to duration, it doesn't matter what happens to interest rates. I'm going to have approximately the same amount at the end. Now, one quick comment on immunization. This is a quick example. It doesn't work quite that precisely because what we assumed here is interest rates changed and then stayed constant after that. In reality, interest rates are always bouncing around. So if we hold till duration, we're not guaranteed to have that payoff, but it gives us an idea of about how long we're going to have to hold the bond until we're not as concerned about interest rate risk. So if we hold a bond to duration, we're going to eliminate a lot of the interest rate risk. Last thing on this video, what happens if I'm not looking at a bond, but instead a bond portfolio? What if I have 50 or 60 bonds in there? How do I calculate the duration of that portfolio? The answer is it's really easy. The duration for a bond portfolio is just equal to the weighted average of the individual bonds' durations. So, quick example I made up. Let's assume we hold 3 bonds. Market value of bond A is $1 million. Market value of bond B is $3 million. Bond C is $4 million. That gives us a total portfolio value of $8 million. Duration is different for each of these bonds. I calculate the weight. 1 million divided by 8 million tells me about 12.5% of my portfolio is in bond A. 3 million divided by 8 million means 37.5% in bond B. And 4 million divided by 8 million means about 50% of my portfolio is in bond C. So then I just take the weight times the duration. It's going to give me this column I called weighted duration. Add them up. Duration for my portfolio is 6.8125 years. So duration for portfolio, it's just a weighted average of the duration for each of the bonds in the portfolio. That's all I've got on duration and convexity. Again, this will probably be more useful if you have the video template there. So I encourage you to take a look at that. It's up on Google Docs. Just real quick again. That was at tinyearl.com, Brocker duration 2, and you'll find this template. Hope that helps. Thank you.